All right, today we are diving into one of the wildest, most surprising connections I've ever come across in science. We're talking about a deep mathematical link between Einstein's theory of general relativity and the AI that helps your phone understand what you're asking it. It's a story that literally connects the cosmos to our conversations.
I mean, just think about this question for a second. What if the math you need to describe black holes was the exact same math that helps your phone figure out you want pizza near me? It sounds completely nuts, right? One is about the fabric of the universe and the other is about, well, language. But as we're about to find out, the core problem in both of these worlds led to the exact same, unbelievably elegant solution.
So, to see how this is even possible, we need to do a little time traveling. We're going to look at two problems that seem to have absolutely nothing to do with each other. One that was breaking physics 100 years ago, and one that's a huge headache for AI engineers right now.
First, let's jump back to 1915. You've got Albert Einstein, and he's staring down a massive problem. See, for centuries, Newton's laws of gravity were considered perfect, but they weren't. Little cracks were showing up. For one, they couldn't quite get the orbit of Mercury right, and they had zero explanation for why light from distant stars seemed to bend when it passed by the sun. The foundations of physics were shaky.
Okay, now let's fast forward to today. AI engineers have a totally different issue. To understand language, an AI turns a sentence into a string of numbers, kind of like a digital fingerprint we call a vector. A standard one has 768 numbers. Now that might not sound like a lot, but when you have to do that for every sentence on the internet, you need giant, expensive data centers just to keep up. It's a brute force method, and honestly, it's hitting a wall.
And here is where it all starts to click. When you put these two problems side by side, the parallels are just stunning. For Einstein, the symptom was predictions that were slightly off. For AI, it's insane costs and memory usage. But underneath it all, both problems force them to ask the exact same wild question. What if the way we think about space itself, what if our geometry is just wrong?
And that leads us to the shared solution, which is just so cool. The answer for both Einstein and for AI wasn't to throw more power at the problem. It wasn't about more complexity. The answer was to completely change the rules of the game. The answer was to embrace a curved reality.
So here's the big idea. We've been trying to map out language, which has this natural tree-like structure, right? You have animal, which branches into mammal, which branches into dog. We've been trying to cram that tree onto a flat grid-like map. It's like trying to organize a library by just throwing all the books on one giant floor. But hyperbolic space, it's different. It naturally expands, exponentially, from the center. It's a space that's already shaped like a tree.
Here's a perfect way to think about it. Using those standard flat vectors is like trying to shove a giant Christmas tree into a square box. To make sure you don't crush all the branches, you'd need a ridiculously huge box, like 768 dimensions huge. But hyperbolic space, it's like a box that was custom-made, already perfectly shaped like a tree. It's just a smarter, more natural fit.
Okay, so the solution is curved space. But what does that even mean? How do you actually do math in a place that's all warped and stretched? Well, it turns out that Einstein and today's AI researchers rely on the exact same two basic tools to find their way around.
The first tool is called the tensor metric. The best way to think about it is like a rule book for your measuring tape. You know, in the normal, flat space we're used to, a foot is a foot no matter where you are. But in curved space, this rule book, the metric, tells you that your measuring tape might actually stretch or shrink depending on where you are in that space. It's a dynamic set of rules for measuring distance.
And you can really see how this works right here. This is a model called a Poincaré Disc. Just look at that stretch factor. When you're near the center, things are pretty normal. But as you move out toward the edge, whoa, the space itself expands like crazy. A tiny little step near the edge actually covers a massive amount of conceptual distance. And that's the magic trick. You can fit an infinite amount of information inside this finite circle, which is perfect for organizing all the endless concepts in language.
All right, the second tool is the geodesic. It sounds fancy, but it's a really simple idea. It's just the shortest possible path between 2 points. We think of that as a straight line, but that's only true on a flat surface. On a globe, right, the shortest path between New York and London is an arc. It's the same thing here. In the curved space of language, the most direct path is a curve.
So, this is the crucial part, the big mind-bending idea. Einstein's breakthrough was realizing gravity isn't a force pulling planets around. The planets are just following the straightest path they can, a geodesic, through space that has been curved by the sun. And in exactly the same way, the similarity between words isn't some magical force pulling them together. It's just geometry. Words that mean similar things are simply close to each other along the natural curved pathways of the space.
Okay, so that's the theory. It sounds amazing, but does it actually work? What happens when you take this century-old math and apply it to a modern AI problem? Well, the results are, honestly, they're just incredible.
A 24 times compression factor. Just let that sink in. By swapping out that clunky 768-dimensional flat space for a sleek 32-dimensional curved space, the amount of data you need just plummets. I mean, that's the difference between needing a giant server and being able to run really smart AI right there on your phone.
But what's the catch? There's got to be a catch, right? You can't shrink something that much without losing a ton of quality. Well, just look at the data. The big standard model scores about 0.834 on quality. The tiny new hyperbolic model, it scores 0.812. That is a nearly invisible 2% dip in quality for a 96% reduction in size. That trade-off is almost unbelievable. It's a total game changer. So this is where we need to zoom out, because what this implies is so much bigger than just writing better code. It suggests there's a fundamental pattern, a shared mathematical language, in how complex systems are built, from the entire cosmos down to the words we use every day.
And this final comparison just brings it all home. It's the same logic. In Einstein's universe, matter tells space-time how to curve. In the AI model, the meaning of words, the semantics, tells the vector space how to curve. Planets follow the shortest path, the geodesic, and when we search for something, our query follows a geodesic to find the most similar answer. Both systems are just trying to find the most efficient state possible. It's the same underlying logic. It's identical.
And that leaves us with this really profound thought. 100 years ago, Einstein figured out the secrets of the cosmos by realizing it was curved. And now, today, by using that very same insight, we're finding a dramatically better way to understand language. It turns out the rules that govern the stars and galaxies are the very same rules that govern our own sentences. The universe and our words, they really do speak the same language, the same mathematics.